Hey, hi, good evening. We're going to intro to kinetics, chemical kinetics. It's the study of reaction, rates of reactions. This is going to look into 5.1 and 5.2 reaction rates and rate laws. We will incorporate units of K because that's part of the rate laws. Important lesson, you need to definitely do your best to follow along, okay? Share screen. Share. All right. So we're going to look at first basic reaction rates. And we would say that the rate of a reaction, first of all, is equal to the change in concentration over time. And within these this equation, rates are relative to stoichiometry. Okay, now I'm going to say reaction rates are relative to stoichiometry. And I'm going to put a big star and say rate laws are not. Okay, so what you need to be realizing is these two things mean different. They are different. They are not the same. Okay, so the rate law is not the same thing as the reaction rate. Okay, so the first thing we are going to talk about are reaction rates, and we will talk about it in terms of this reaction that we have here. So the rate of reaction for what we have up above, reaction, let's spell that correctly, is equal to negative the change in the concentration of X, and that would be the final concentration minus the initial concentration. And because X and XY are products, they are reactants, we will be losing them. Thus, we have a negative sign here because the final X of F will be less than the initial, which would cause that change to be negative. And we do not want the overall rate to be negative. So we place the negative sign here to ensure that we actually have a positive value for our rate. We will divide that by the time. And because there is a 3 here, let me get a color, because there's a 3 here, we will put a 3 here because this is relative, okay? That would be equal to our next reactant. And because it's a reactant, it will also be negative, and that will be in the change of concentration of X, Y, minus X, Y, initial. And we will divide that by time, and we will put a 2 here due to the exponent that we have here. Okay, so that will be there. All right, and we will then set that equal to, and this time it will be positive because we have a product and we are gaining it. So the change in concentration when we do the final concentration of X3, Y2 minus the initial concentration of X3, Y2, it will be a positive value. So we do not need to put a negative in front of it to cause it to be a positive value. And because there is a 1 here, there is an understood 1 there, okay? So those are your relative rates of reaction. We could apply that to a problem. that would look like this. Here, okay? Nope, it's not gonna look like that there. My bad. Okay, I'll make up my own. I'm sorry about that. I will make up my own. Okay, so let's say that in this reaction that the rate of consumption of X is 2.0 times 10 to the negative 1 moles per liter second, okay? Okay, well, what is the rate of consumption of reactants and all products? Okay, well, this is real simple because we've said that it is based on stoichiometry, right? So we will just look at the stoichiometry of it. And if it is 2.0 times 10 to the negative first moles per liter second, and that would be moles of X. And according to the stoichiometry, there's 3 moles of X for every 2 moles of X, Y. If we were to do that, we would end up with 1.3 or times 10 to the negative 1. I'm sorry. There we go. Times 10 to the negative 1 moles of X, Y over liters per second, which would give us a rate of 1.3 times 10 to the negative 1 molars per second, or moles per liter second. And there's several different ways you could go about writing that, okay? So that relates X and XY. Sorry about the weird, yeah, let's just make, yeah, don't pay too close attention at that. It's not even really balanced. I'm not worried about it. Well, let's see, we should balance it. We would put a 2 here, and a 6 here. No, it's impossible to balance. Don't even worry about it. Just leave it the way it is and don't look at it, okay? Just don't even look at it. It's working. It's working. It's working. Please be. Just please let it be. Please let it be. We can go back and fix it later. 2.0 times 10 to the negative 1 moles of X for every liter second. And we want to know the rate of production of this. Well, it's at 3 moles to 1 mole. Okay, so that's 3 moles of X to 1 mole of, what do we call that? X3, Y2. And we get, what's 2 divided by 3.67? That's 1 divided by 3, 1.3. It's 2 divided by 3, 1.3. How am I supposed to know that? Real easy. I was right the first time, 0.67. There, 0.67 moles per second of X3, Y2. So notice that the rate of reaction is the concentration, how much of it is reacting per unit of time. Okay, concentration of reactant, how much of it is reacting per unit of time. Okay, and that's easy. Now, what we have next is something called a rate law. Okay, And what a rate law does is it shows how a change in concentration of a reactant affects the rate. Okay? Okay, and rate laws must be determined experimentally. Right? They must be determined experimentally. And it's really easy to do it. And we do it by something called the initial rates method. Okay, and when we use the initial rates method, we're going to find out if a order of reaction, if it is zero, oops, I don't want that. If it is zero order, we will find out if it is first order, if a reactant is zero order. If a reactant is first order, we will find out if a reactant is second order. Okay? So in our equation up above, we could say that it is zero order with respect to 3x, and it is first order with respect to xy. We would not talk about this species because it is not a reactant, so its concentration will not affect the rate of the reaction. The order of reaction has nothing to do with the stoichiometry. Okay? It must be determined experimentally, and we will look at how that is done here in just a second. Let's first talk about what these terms mean. Okay? So if we find out that a reaction is zero order with respect to a given reactant, what that means is the concentration does not or affect, is that an affect or an effect? The rate. Okay? There's no correlation, no cause-effect relationship. It's an effect relationship. So if I double the concentration, nothing happens to the rate, okay? For a first order, we have a direct relationship. Whatever I do to the concentration, I also do to the rate, right? Double concentration, double rate. They're directly related. Second order, 1, 1, 2, 4, I have a kind of an exponential sort of relationship, but if I double the concentration, the rate goes up by 4. And I will show you more about that later. Okay? Okay, I'll explain that later when I can show you an example of how to figure it out and you'll understand what I'm talking about. Okay, now let's look at an example of the initial rates method and how to use this method to determine a rate law for a given reaction at a given temperature. Before we look at it, let's talk about it. Let's say that we've got an equation. A, B, well, let's just go like this. Let's just go A plus B yields A, B, okay? And let's look at how we could set up a reaction to determine how the concentration affects the rate. Well, I would set up several different experiments, okay? And in the first experiment, I would have the concentration of A change, and I would have the concentration of A change, and I would have the concentration of B stay the same, and I would have the concentration of B stay the same. And then I would measure the rate of the reaction. At a given moment in time, I would find out how much is present, how much is not present, okay? And what that means is I would compare rate 1 to rate 2, and I would look at the actual values, and I would relate them to the change that occurred over here. And I would see how they were related. And I would know that whatever change happened to my rate was not due to reactant B, because reactant B didn't change. I would then set up 2 more experiments, and I would keep these concentrations the same throughout. And these are concentrations. And I would change the concentration of B, okay? And once again, I would look at the rates, and I would see how the change in the concentration of B affected the change in the rate. And I would know that none of the change here was due to A, because A stayed the same. So that's the idea behind it, okay? So let's now go look at some practice problems. And those are going to be right here. Okay. So an initial rate law method is going to have typically some data that looks like this. Okay? This is what it's going to look like. Here are your experiments. Here's the concentrations of X. Here's the concentrations of Y. Here's the rate for each experiment. All right? So the typical questions that come with it are represented right here. So let's just look at one of these. What is the order of reactant X? Okay, well, I'm going to look up here at X. I'm going to find where Y is constant and X is changing. And I see that as experiment 3 and experiment 1. I like the fact that Y is not changing and X is changing, such that whatever is happening to the rate is fully due to the change in concentration of X. So what I'm going to do is I'm going to put experiment 3 over experiment 1, because experiment 3 has a larger concentration, and I like my large number to be on top. Okay, and I'm going to write that that's equal to the concentration of X in experiment 3 over the concentration of X in experiment 1, raised to a number that we'll call A, I don't know, and make it equal to rate 3 over rate 1 every time. So in experiment 3, I've got a concentration of X at 0.20. I've got a concentration in experiment 1 of X of 0.10. I will divide those, raise it to a number. I don't want to call that A. Let's just call it, I don't know, X. Let's call it X. And that's equal to the rate, 4.0, divided by the other rate. I can put the constants in there, but I don't have to. Look how easy this is. 0.2 divided by 0.1 is 2 raised to the X equals 1. I'm pretty sure that anything raised to the 0 is 1. So X must be 0. Therefore, this is 0 order with respect to X. Okay? So then that makes sense, because when we changed the concentration of X, it did not affect the rate. And that's what it means to be 0 order. Your concentration does not affect the rate. What is the order of reactant Y? Okay, well, we need Y to change and X to stay the same. Now, every now and again, that won't happen. Okay? And I'll bring up an example like that in class. Please remind me. I'll be prepared for it, hopefully. Experiment 1 has Y at 0.2. I like the larger number to be on top, the larger concentration because it allows me to have a number greater than 1. And I'm going to put that and put a y out here, and I'm going to set it equal to 4 divided by 1. And what I get is 0.2 divided by 0.1 is 2 raised to the y equals 4, y equals 2. Okay, so therefore, I don't need to put that, guys. This is second order with, I'm going to go with respect to, okay, clean that up a little bit, with respect to, with respect to y. Okay, so we've got a 0 order and we've got a second order. What is the overall order? Okay, that's each individual order added up. That's all. So the overall order is 0 plus 2 equals second order overall. Okay, write the rate law. Okay, the rate law always starts with rate equals. There's then a K. This is a lowercase k. This is a rate constant. Okay, it's constant for a given reaction at a given temperature. You then include the reactants in their orders of reaction as superscripts. However, if the order of reaction is 0, you exclude it from the rate law such that it should not be present. And we have our rate equals K, our rate constant, concentration of Y squared. That is our rate law. It is not our reaction or rate of reaction. It is our rate law. It tells us how the concentration affects the rate. Find the value of the rate constant, K. Pick any experiment. And plug data into the rate law. Okay, once again, the rate law is experimentally determined, and we will pick our experimental data from any reaction experiment up here we want, and we will plug it in to the rate law and solve for K. So we've got X is 0.1 and Y is 0.2, and the rate is 4. So we have rate equals KX squared. 4.0 moles per liter second equals K. What was X? 0.1. 0.10 squared. Let's clean that up. I don't like those units. That looks nicer and neater than the other. Looks much better. Okay, so let's start simplifying. Let's square the 0.1, right? You could do that. What is that, 0.01? And then we'll divide 4 by 0.01. And what is that? Yeah, 400. So we've got 400 equals K. I think I did that right. Okay. I think that looks good. Equals K. And then, okay. Oh, now we need to have some units with K. Well, this was a moles per liter squared. We divided this by moles per liter squared, that gives us a liter per mole. And then we have our time, second. So K equals 400. I hope that number is right. I feel like something's wrong with it. Per moles per second. Or K equals 400 liters per mole second. Okay? Ask questions if you have it. Find the rate of the reaction, not the rate law, when X and Y equal. Okay, well, we know that the rate, according to the rate law, is equal to K, concentration of X squared. Okay? Oh my gosh. It's Y squared. That's why I got a different number. Do I just go with it? Do I just go with it? That this right here was supposed to be Y all along. And it was because it was Y, it was 0.2 and not 0.1. Can I just go with it? 0.2, because I have too much to do. 0.2 times 0.2 is what, 0.04? And this becomes 100, 100, 100. I'm moving on. I'm moving on. This is why I just saw that. I knew that number didn't. Okay. All right. Thank you. Rate equals KY squared. We need to know the rate when this is at a particular concentration. It does not matter what the concentration of X is because the concentration of X does not affect the rate. So we don't need that information. So we're going to solve for the rate. Same equation, same temperature. We'll plug in our rate constant. Okay. We'll plug in our concentration of Y, which is now 0.25, and we'll square it. So 0.25 squared equals times 100 equals 6.25. Okay. So you might want to go through that again. Now, if you want to look more at, should we do another one? Okay, what is the order with respect to CH3CBr? This guy here. All right, well, we want him to change and him to stay the same. I like the big one on top. So I'm going to do experiment 3 over experiment 2. I'm going to do 1 times 10 to the negative 1 over 5 times 10 to the negative 2 equals 4 times 10 to the negative 6 over 2 times 10 to the negative 6. 1 divided by 5 is what? 0.2. 0.2. Or that's 2. My bad. 2 equals 2x equals 1 first order with respect to x. H2O, we want H2O to change and these to stay the same. We'll put experiment 2 on top. So we've got experiment 2 over experiment 1 equals 4 over 2. raised to a number, would be a different number. And this is going to be 1 because these are the same thing. So we've got 4 divided by 2 is 2 raised to the y equals 1. Anything raised to the 0, so this is 0 order with respect to y. What is the overall order? First order, right? Because we have a 0 plus a 1. Right, the rate law, rate equals k. First order with respect to CH3, 3BR. We don't need to incorporate the water because it's 0 order. Calculate the rate constant, pick any experiment, plug the information into the rate law. So we've got rate is 2.0 times 10 to the negative 6 moles per liter second equals K. And then we've got this concentration, which is 5.0 times 10 to the negative second. And that is just itself. It's not divided by or raised to anything. So 2.0 second E negative 6 divided by 5.0 second E negative 2 equals 4.0 times 10 to the negative 5th. Now we had a moles per liter second divided by a moles per liter. So that leaves me with a per second. Boom. You must know units for K. I'll probably give you a pop quiz in class. So I can give you a hint. Actually, I put it in another video. But kinetics is good stuff, and we're actually almost halfway through with this unit. It's a really short unit. It's really straight to the point. It's not wishy-washy. It's good stuff. I hope you understood that. I do. Every now and again, you can't find everything. There's one of the concentrations doesn't change. So I will have to be sure to bring one of those to class with us to look at. You just have to think through it a little bit further. Okay. Right on. It's great. See you later.